This problem and all other data structure problems can be found here at Sarai Studies. Link is in the description box below. Below is an array representing a binary heap for a min heap. Show the array contents after delete min. So in other words, we're just deleting the minimum key in this array, or binary heap, tree, priority queue, whatever you want to call it. So first, let's actually convert this into a tree. I look at my last key, I go up and I see the index, it's 14. That tells me how many nodes I'm going to need. So I need 14 nodes. I know it's a binary tree, so every node is going to have 2 children. So I'm just going to keep adding 2 children until I get to 14. Right now I have 7, so then 8, 9, 10, 11, 12, 13, and then 14. Then I split the tree into rows or levels to help me start numbering the nodes. The way that I start numbering is I just number from left to right 1, 2, 3, 4 until I run out of nodes, and then I move on to the next row. So in this case, there's only 1, then I run out of nodes, I move on to the next row. 2, 3, so from left to right, I run out of nodes, I move on to the next row. 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14. And then my array tells me that at index 1, the key is going to be 1. My array tells me that at index 2, the key is going to be 3. Or you can just look at this and write the numbers in order, starting from the first row from left to right, and then when you run out of nodes, go to the next row, the same way that we numbered it. So then it's 2, I run out of nodes, then I go 7, 5, 9, 6 in the next row. I run out of nodes, so I go 7, 11, 20, 14, 18, 12, and 20 again. Now this is just the tree that they gave to us. We actually have to show the tree when we delete the minimum value. So first let's identify what that is. In this case, that's 1. And anytime we're deleting, we always swap with the last key. So in that case, that would be this one over here. So we're swapping 1 and 20. And because this is a delete method, we have to delete the last one. So the second step is to delete the last node. So this here just becomes null. Probably should have specified this one over here as well. But then we have a problem. This is a min heap. What's the property of a min heap? Well, both min and max are based on the parent. So what about the parent? The parent is always smaller. So min smaller. Smaller than or equal to both of its children. But if you take a look at this subtree over here, the parent here is 20. It's not smaller than 3 and 2. So it's violating the property of a min heap. And this is a min heap. Keep it that way. So what can we do to fix it? Well, we would have to sink 20 down. When we have this 20 and we want to bring it down, the only way it can go down is either by swapping with the 3 or swapping with the 2. Which one do we prefer? If it's a min heap, we want the smaller numbers at the top. Well, let's swap with 2 because then that is going to be the smaller number at the top. You can also think min smaller. So we swap 20 and 2, but then you look at the subtree. Is this parent smaller than or equal to both of its children? No, it's actually bigger. It's a problem. So we continue sinking down 20 by swapping with a smaller child, I should say. In that case, the smaller child is 6. So we're going to swap 6 and 20. Now you look at this tree. Is this parent smaller than or equal to both of its children? Yes. Good. Then you look at the other subtree associated with the one we changed. Is this parent smaller or equal to both of its children? Well, it's irrelevant. So you can stop sinking either when the property here is satisfied or you end up with your key in a leaf node. A leaf node is one whose links are both null because it's irrelevant, right? This parent, it doesn't matter if it's smaller than or equal to nodes that don't exist anyway. So we're good. We can stop right here, and they want the array content. So we're going to have to rewrite that again in an array. So we never start at 0. Remember that. And after that's pretty easy. It literally tells you at index 1, the number, the key is going to be 2. At index 2, the number, the key is going to be 3. Or you could just literally go row by row from left to right and just write the numbers. So then I see 6, move on to the next row, 7, 5, 9, 20. Then I move on to the next row, 7, 11, 20. 14, 18, 12. So we started with 14, we ended up with 13 nodes, and that makes sense because we deleted a node. And that's it for this video. I'll see you in the next.